Okay, good morning, everyone. Hope you had a great weekend. It's our first full week of class, and what we'll be doing today is finishing up 3.5. I just need to do one word problem in there. We're also going to do 3.6 hyperbolic functions. Next class, we kind of get into the antiderivatives and really start to shift our focus on getting on the track to the main Cal 2 material. Wanted to do a real quick recap of what we talked about last time. So from last class, the main idea is that we established 6 new functions, or well, the functions we had established in pre-cal, the inverse trig functions. We just established that each of those 6 inverse trig functions have derivatives. And I gave you the where it is in the formula sheet. We derived where these come from for a few of these, not all of them. In doing so, we also established the idea of a reference triangle and how that will come up later. And then we practiced using the chain rule and implicit differentiation with those new trig functions, or those new derivatives, I should say. Okay, so that's what last class was about. Today, what we're going to be doing is we're going to be establishing, first we have to establish 12 new functions today, all right? New functions that you haven't dealt with in the past. And then once we establish those 12 functions, each one of them has derivatives. So we actually have 24 new functions today, the 12 functions and their derivatives, all right? Now, it's actually gonna go pretty fast. It's not gonna take forever to do it. So the 12 functions we're gonna deal with are first the 6, what we call hyperbolic functions, okay? We established these 6 hyperbolic functions, and then we established their inverses, and then each of those have derivatives. So each of the 6 hyperbolic functions have derivatives. Each of the 6 hyperbolic inverse functions have derivatives. And once we complete that, we will have all the functions we need to proceed on through calculus. So it's kind of like after today, there's no new functions that we're going to learn. We've got all the trig functions from pre-cal. We've got the exponential logarithmic functions from college algebra. We've got all these inverses. We've got the hyperbolics. We've got the inverse hyperbolics, and we basically have got it all. Okay, and then we just crank through the rest of calculus. So once we establish these 12, we will differentiate them, and we'll see an application of a hyperbolic. Okay, so that's the plan, but stay true to keeping you on your toes. We're gonna start with the quiz. So I have 2 problems here for you. It's multiple choice. First one, I want you to find the derivative of this function. Here are your choices for answers. And then on the second one, I give you an implicit equation. And I want to know, if you take the derivative with respect to x, which of these would be correct? So if I ask you to take derivative of this with respect to x, which of these 4 would be correct? And I'm not asking you to simplify. I just want to know which of these derivatives would be right. And I'm going to send a poll out right now. You have your choice options there. And I don't know, I'm not sure how much time I'm going to give you. So just work quickly. I'll just take a look at how many responses I have and go from there, but no more than 10 minutes, no more. Enjoy. You're not going to turn this in. I'm just going to go strictly off the poll, but make sure you do write down your work.
Hey, Professor.
I'm sorry, did someone say something?
Yeah, me. So I'm on my phone, and that poll that just came up for me to answer, I just put A in for both because I had no idea what was going. I had no idea what was going on.
Oh, well,
Are we doing a quiz right now?
yeah, do you see the problems? Can you see the problems or no? Joshua, can you see the two problems?
Yeah. I see them.
Okay,
Yeah.
yes. So you're supposed to work those out and choose, A, B, C, or D for each one on the poll.
Oh, okay. All right.
We just
How much
started.
time do we have?
We're 2 minutes into this.
Okay, fantastic. Sorry, I was a
Okay.
little late. So thank
It
you.
should let you change your answer if you need to.
Okay.
All right.
Professor, I was going to ask you a question.
Yes.
How do we know how far we go with simplify?
Well, you got to go far enough to see the correct answer.
So just like as far as we can.
Well, as you're working through, I'd be looking at your options and seeing if you've got one of them there.
Oh no, oh sorry, I didn't mean just for these. Like because there was some like homework problems.
Oh, in general.
Yeah, in general.
You should be able to just take the derivative and have the derivative, but you should also be able to manipulate it, algebraically. I would say for a test, you just got to get the differentiation correct.
Okay.
Unless the problem requires that you go further, like solving it, setting it equal to 0 or something.
Okay.
Yeah. We're 6 minutes in. We have 7 of 18 have replied to both questions. We'll go 3 more minutes. Okay, we have 1 minute left.
The poll just disappeared from my screen. I don't know why.
I'm sorry, Lauren, I didn't hear what you said.
I said the poll just disappeared from my screen.
Yeah, I'm not sure how to find the poll either at this point.
Okay, then just send your answers in the chat. Make sure you send me answers to both questions. Okay. All right, that's gonna be time. I'm gonna end the poll. 5, 4, 3, 2, 1. Okay. So the results, I'm sharing the results. Problem number 1, 81% of you chose B, that is correct. And for number 2, 69% of you chose D, that is correct. So the correct answers were B and D. All right, so that'll be your first quiz grade. And this is just an example of one type of thing I could do for quizzes, just to kind of keep you on your toes with things. On the first, I'm going to work through it real quick. On the first one, we're using the fact that if you take the derivative of sine inverse of x, that the derivative is 1 over the square root of 1 minus x squared. And so for us here, the x is actually all this crap in here in yellow. So the first thing we have to do is take I'm gonna do it down here, 1 over the square root of 1 minus all of this stuff in yellow squared. And when you square it, the square root goes away, so you don't have that anymore. But then you distribute the negative through, so it's really 1 minus 2x minus 1. And the ones cancel, and you just get a negative 2x under a root. So that's this part. But because chain rule, you then have to take derivative of what's in here. And the derivative of the square root of something is 1 over 2 times the square root of whatever was in there. And then chain rule continuing, multiply that times the derivative of what's inside, which is 2. And the 2's cancel. So that gives you that piece. Now on the second one, we're doing the derivative of arctangent of something, and the derivative of arctangent of x through the formula is 1 over 1 plus x squared. And so for us, the x is actually all of this junk in here. So it'll be 1 over 1 plus all of that junk in yellow squared. So it could be this answer. Could be any of those. Those are all correct. But then you have chain rule. You have to take derivative of what's in here. So when you take derivative of what's in here, because you have addition, you have to take derivative of x first with respect to x. I said this was with respect to x. So derivative, that's 1. So it could be any of these guys. Plus the derivative of y squared. That's also chain rule. First, you have to do 2y, right? But then you have to take derivative of y itself, which is y prime. So it's got to be, it can't be this one. It's got to be this one or this one. So these two look like we're on the right track. And then you have to take derivative of the right side, which is a product rule. So you take derivative of x squared, which is 2x, but then times y, that's this, and then plus the derivative of y, which is y prime times x squared, which is this. So this one's off just a little bit. So D and B. Okay. Questions? All right. We move on to today's material then. I have lecture notes that I'm going to bring up. 3.5, there was one problem at the end we didn't have a chance to do. And that's this problem with this rocket being fired. So I wanted to take some time to go through this one. A rocket is fired straight up with speed of 1,000 miles an hour. An observer who's a mile away from the launch point is tracking the rocket with binoculars. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? What is that in degrees per second? So I'm gonna take this over here and paste it in here. So I know for my Cal 1 students, the students who had me for Cal 1, this is a related rate problem. And I gave my Cal 1 students like a template of how to go about related rate problems. And that template is useful for like getting used to how related rate problems work. If you want access to that, I can send it. Let me actually, let's see if I download it. Go quick here. Give me a second, sorry. That's going to take too long. I'll send it to you all later. I have a template. It looks like this. It's like a worksheet, and basically it kind of reminds you of the steps for doing related rates, that you're going to draw some pictures, you're going to figure out what you're given, what you want, you come up with some equation. So this all depends on your background in Cal 1, how you were taught related rates. So when I'm presenting this right now, I'm going to be going through it the way I kind of would have done it in a Cal 1 class, right? So if it seems different to you, I'm just kind of letting you know, I know it might be different because of the way you were taught. So I always tell my students, when you have related rate problem, you first draw a picture of the situation in what's called the general picture. And then I tell my students, and then you'll have a picture of like the instant in time. So the difference between these two pictures is the general picture, you have to imagine that everything is in motion. And then the instant picture is like the moment in time that the question is asking you to like take a snapshot. So here's my picture. I've got the ground. I've got a rocket that's been fired straight up. So I've got this rocket that's traveling this direction. Here's my little rocket. Okay, let's blast off there. There we go. And it's fired straight up. I know that it's going 1,000 miles per hour. I have an observer who's a mile away from the launch point. So I've got some person here on the ground that's watching this happen. That's 1 mile. And that's what's going on, right? That's what's happening. Rocket's going up, observers watching it. Now, the instant in time that we're talking about, we have this rocket that now has traveled to a specific height, right? 3 miles high. So at the specific instant we're talking about, this is 3 miles. The observer is still standing here 1 mile away, right? So I'm kind of fixing everything in time right there. I want to know what I'm given. I want to know what I want. And then I'll want an equation that connects everything together. So I'm given a couple of things. I'm given the speed of the rocket, right? The speed of the rocket. So the speed is always going to be a derivative. So I'm going to label the distance, very important here, the distance from here to here. I'm going to label that anything I want. Let's call it h for the height of the rocket. Okay, so h is the height of the rocket. So what I'm given when I'm given this speed is I'm given how fast h is changing with respect to time. So I could write dh dt is given to me to be 1,000 miles per hour. Are there any questions? The rate at which h is changing with respect to time is 1,000 miles per hour. What do I want in the question? What is this question asking me to find?
The degrees per second.
Yeah, it's asking how fast the observer's angle of inclination is changing. So I need to label that on my picture. I need somewhere in here the angle of inclination. So the observer's watching the rocket. And when it watches the rocket, it creates an angle with the ground called theta. So imagine it's like the head, the person's head, right, is tilting as it's watching the rocket go up. That's the angle of inclination. I want to know how fast it's changing. So I want to know the rate of change, the derivative with respect to time of the angle. I want to know what that is. And I want to know that at exactly the moment. At what moment? At the moment the rocket is 3 miles high, right? So what is 3 miles high means that I want to know what's happening with that angle at exactly the moment. What's 3? In my picture, what is 3?
The height.
The height, right? H. So I want to know how fast it's changing at height of 3 miles. So I've got my general picture. Everything's moving here. Here's the snapshot in time. Here's what I'm given. Here's what I want. And now the very important part of the problem is to come up with an equation, right? An equation that connects H and theta together. And you are only allowed in this part of the problem when you're coming up with your equation. You can only be looking at the general picture. You cannot be looking at the snapshot. So who has an equation that relates H and theta together?
Isn't it something to do with tangent?
Tangent, right? H is, here's theta, here's H. H is the opposite side of this
Yeah.
angle,
and we
right?
have
The
adjacent.
opposite. And we have the adjacent, right? We know what the adjacent is. The adjacent is 1, it never changes. So it'd be very useful for me to be using opposite and adjacent, wouldn't it? Yes? Okay, so let's do that. I can write down this relationship that tangent of that angle theta is equal to H over 1, which really just means that tangent of theta is H. Are there any questions? I realize related rates is not something people feel comfortable with in Cal 1. It's weird. Are y'all following what I'm doing here?
Yes, sir.
Okay. What's the next step? We have the equation, right? It connects theta and H together. So what do we do now that we have the equation? We want to know dH dt and d theta dt, right? We want to know how these variables change with respect to time. So what am I going to do with the equation? You'll look stunned. You look like me after that football game last night.
Hunter had said in the chat to take the derivative.
We're going to take the derivative of that equation with respect to what variable?
Theta
Well,
or time?
look at both of our differentials here. They're both with respect to time, aren't they? So we want to differentiate this equation with respect to time. That way we get a dH dt and a d theta dt to come out, right? So I'm going to go with this equation. I'm going to take the derivative with respect to time on the left side and the derivative with respect to time on the right side. This is the implicit differentiation step. Okay, so now I'm doing implicit here. And like I said, that little cheat sheet that I give my Cal 1 students, you know, we draw the instant in time, the general picture. What do we give them? What do we want? Here's the equation, implicit derivative. We have to take the implicit derivative. And then the rest of this is just so we can do scratch work. But let's see here. So I need the derivative. Okay, good. This should be not that bad. What's the derivative of tangent theta with respect to time? Brandon, are you there?
Yes, I'm.
Okay. All right, Brandon. Carefully, Brandon. Give me the derivative of tangent of theta with respect to time. So, Brandon, what's a derivative of tangent of anything?
Secant squared.
Secant squared of that theta, right?
Yeah.
Good. Now, chain rule, times. Now, Brandon, what is the derivative of theta with respect to time?
Channel. We just
Isn't
Yeah.
that just d theta dt? Like,
yeah.
I mean, that's what it is. It's d theta dt, right? We actually don't know what that is, Brandon, do we? But isn't that what we're searching for? Isn't that what we want?
Yes.
Yeah, so it's very good for us to see it appear in the equation, right? After we take derivative, because that's actually what we're going to be solving for. But it only appears if you remember that there's chain rule involved here, right? If you just take derivative of tangent theta, put secant squared theta, and never put the d theta dt, you're never going to be able to solve for it. Okay, equals, okay, right side, Carlos. Carlos L. Carlos L, no?
Yes, yes,
Okay.
right here.
So what's the derivative of h with respect to time?
Just one.
It would be one if it was h on the top and the bottom, right? If it was h here and h here, then the answer would be one. But because it's h and t, it's just dh dt, right? Like that's all it is. It's
Oh,
not
okay.
one, right? It's just
Like-
dh
Like
dt.
it will be like, for example, the dx and y, it'll be like y prime, like.
Yeah, exactly. It'd be
Okay.
like y prime. This is kind of like an h prime, but this notation is
Okay.
better because we're keeping track of the variable on the bottom, right? T.
All right.
But see, Carlos, we're actually not, we're not upset about this because this right here, DHDT, we know what it is, don't we? It's 1,000. So we know
Yes.
DHDT is going to be replaced with 1,000. We're trying to solve for d theta dt, right? The only thing we really would need to know now is what theta is, right? If I somehow knew what theta was, I could figure out what secant squared of that angle was, and then I'd be able to solve this. Do y'all understand that? This right here is 1,000. D theta dt is what we're solving for. If we just knew this theta, if we just knew what that was, then I could figure out what that is, and it would just be a number, wouldn't it?
So do we move that to the other side?
We can move it to the other side. Yeah, we'll have to move it to the other side, the secant squared theta. We'd have to move it to the other side, but I need to know what theta is. So this is where you're allowed to go and look now at the instant in time, right? You can now look here and you can say, oh, look, I'm trying to figure out what this angle is. But see, now we have 3 and 1, don't we? So we can actually figure out what that angle is. Y'all following me?
Yes.
So let me just recap this problem. We drew a picture. We figured out what we're given, what we want. We found the equation, very important. We found this equation. We differentiate it with respect to time. We got our d theta dt, dh dt. The big issue for us right now to solve this problem, we have to know what theta is, right? And that's going to require some more work. Agree? 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 Okay.
Yes.
So what does this have to do with inverse trig functions? That's what this section is about, right? Inverse trig functions and their derivatives. What does this have that, like, why is this here? Here's why. Watch. I'm going to go back to this equation right here. You know how we differentiated it here and did all this work, right? Let's not do that. Watch what I'm going to do first. I'm going to take tangent inverse on both sides of this equation. Okay, I'm going to take tangent inverse on the left side and tangent inverse on the right side. And I'm sure you're sitting there going, why do that? Why bring in an inverse trig function? It's going to make things more complicated. Just bear with me, all right? What does the left side become?
Just theta.
Those two kill each other, don't they?
Just theta, yeah.
Just theta, okay? And the right side is, well, tangent inverse of h. Okay, good. Well, this is an equation too, right? I mean, these two equations are equivalent, right? One of them is tangent theta equals h. The other one is tangent inverse of h equals theta. But they're both an equation that connect theta and h together, yeah? Now differentiate with respect to time. Now do it. So what would the derivative on the left side be with respect to time? Christopher? If you go by something else, let me know. Like if you go by Chris or something, Christopher M? No. I see Chris M. I see Chris. I don't hear Chris. Okay. How about Lewis? Lewis.
Yes, sir.
Okay, help me out with this derivative. We're differentiating with respect to time here. So what's the derivative of theta with respect to time?
D theta divided by dt.
Yep, okay, and that's it, right? And we're happy to see that, right? Because it's actually what we're looking for in the problem. All right, good. You want to keep going with this? What's the derivative of arctangent of h?
It's 1 divided by 1 plus x squared.
Plus, in this case, h squared.
H squared, yeah.
Very good, almost done. Careful, one more little thing. Chain rule.
Those are just 1. Or actually, it'd be d sub h divided by dct.
dh dt.
Yeah.
Good. So Lewis is saying, all right, derivative of arctangent of something is 1 over 1 plus that something squared times chain rule derivative of h with respect to time is dh dt. What is the difference between this and the one we did over here? What's the big difference?
We know both variables.
Well,
We know what dh
yeah,
and dt is, and we know what h is.
We know,
exactly.
yeah.
So dh dt we know is 1,000, right?
Mhm,
The theta dt we're solving for.
mhm.
And so the only thing we need to know in order to answer this problem is what h is, right?
We already know it.
But we know it, right? We actually don't need theta at all, which means we don't need to go solve it and do any work. Do y'all see that doing it this way saved us from having to go figure out what theta was? We just use h. So I think it's easy for me to do this answer now. D theta dt should be equal to 1 over 1 plus, what was h? We had it written down, 3, right? So 3 squared is 9 times dh dt is 1,000. So this should be 1/10 times 1,000. This is 100 is d theta dt. And this is the change in angle with respect to time. So our unit should be the angle is measured in radians. And the time here is measured in hours. So at that particular instant that the rocket is 3 miles high, the observer's angle of inclination is changing at an instantaneous rate of 100 radians per hour. See, didn't need theta. If you go back and you do this problem right here and figure out what theta is and do all the work, you'll get the same answer. Okay, we'll get the same result. It's just I never had to go get theta. It's just more efficient. Now, I did ask in this problem for us to give the answer in degrees per second, right? I wanted the answer in degrees per second. And right now we're in radians per hour. So this is just to remind you of how we convert. So I'd write this as, I'm going to put rad over 1 hour. And I want to get it to degrees per second. So let's get radians to degrees first. How do you convert a radian to a degree? What's the conversion?
180
There's 180 degrees and how many radians?
and 1. No. Pi? No.
Pi radians.
Yeah,
Pi radians. Pi radians. So here's what I'm going to do. Put 180 degrees and divide it by pi radians. That will allow me to cancel the radians out. And then I also need to get hours to seconds, right? So I can do that several ways. I can do this. 1 hour is 60 minutes. And then I can put 1 minute is 60 seconds. I could do something like that. And that would allow me to cancel my hour units and my minute units. And all I'd be left with at the end of all of this is degrees, and degrees on top and seconds on the bottom. So I'm multiplying 100 times 180 on top. That's what, 1800 degrees over, and now I have to do 1 times pi times 60 times 60. I don't have a calculator. We're going to get a decimal answer because this is going to be a decimal.
Pi.
I'm sorry.
Oh no, I thought it was pi 360 for the bottom.
It's 11,309.
Yeah, I've got about 11,309, something like that, close. Take 1800 and divide it by that. And you get approximately 0.16 degrees per second. Okay, that was just an exercise to just remind you how we do like conversions called like dimensional analysis, where you change like from one unit to another. Plus, degrees per second is a little bit easier for us to kind of wrap our heads around. All right, that's it. I just wanted to show you that one word problem because it kind of like stirs up related rates and how we do that. Good news, we aren't doing any more related rates in here. You're not going to have a bunch of related rate problems, but this just shows you the main point of this is to show you how, if you just think about this a little bit, think about what you have and what you don't have, doing this little arctan first kind of saves you time. Makes it a little easier. All right, we're done. That's it for 3.5. You can try that last word problem. What was it, number 39? I think I said to wait on. That was a related rate problem. So you can go check that one out if you'd like now. As far as submitting the homework, I believe that that was due, right? How did that go for y'all?
Pretty good.
Yeah.
I ended up like trying them out, and if I didn't do well, I would just go over the problem on the YouTube video.
Yeah.
Yeah, same
The
thing.
next one's not due till next week, right? There's nothing due.
Right.
I believe, if I'm not
So the
mistaken.
30th. Yeah.
Yeah, I believe it is. Let me see here. Yeah, I believe it's, so there's nothing due. So 3.5, that handwritten homework, the next one's the 30th, and it's 3.6. That doesn't make sense. Hold on.
It's
No, no, no.
3.6 and 4.7.
And 4.7, there's both of them in there?
Yes.
Yeah, I was gonna say there should be another one in there. I don't know why it's not listing it here. Let me just look real quick. Assignments. Oh, I'm sorry. The title of it's 3.6 and 4.7. So it's both of those. Yeah, both of those are due Sunday night. So if you're going to watch football on Sunday, maybe get it done before. All right, here we go. Moving on. So let's talk about these new functions called hyperbolic functions or hyperbolic trig functions. It's weird because these hyperbolic function, they're called hyperbolic trig functions or hyperbolic trigonometric functions. So you would think that they somehow involve like sine or cosine or something like that. Turns out that they don't. Okay, they do not involve sine or cosine. In fact, they involve the exponential function e to the x. So I have to first define what the hyperbolic functions are. So there are 6 additional trig functions. Again, we're calling them trig functions, hyperbolic trig functions, but they are just some special form combination of e to the x and e to the negative x. So it's really kind of a strange thing. It turns out that e to the x, we all recognize from college algebra, and e to the negative x, which is just its reflection over the y-axis. There are a lot of times in different branches of science that these two functions appear together in expressions. And it happens so often that we have special names for when they appear and they look a certain way. All right. So it's kind of like we just kept on seeing these show up a lot, and then we just started to give them a name. All right. So let me they're all just combinations of those two functions. So the first one is this one right here. Notice it's sine, but then we put an h next to it. That lets you know we're talking about the hyperbolic sine function. And it's the hyperbolic sine of x. And here's the definition of it. I'll make this a little bigger for you. The definition of sine hyperbolic x is that it's e to the x minus e to the negative x, all divided by 2. Or if you like, you could pull the 2 out in front and you could say it's half of e to the x minus e to the negative x. Let's go look at it. You want to go see what it looks like? Remember, all that's in your notes, okay? So you don't have to sit here and copy all this down. 0.5, okay, I'm going to do 0.5. No, I'm not. I'm going to do 1/2. And then I'm going to do e to the x minus e to the negative x. And that's it. That is the sine hyperbolic function. What are some things that you can note that you notice about it that's different than like your regular sine function from pre-calc? Let me zoom out on it.
It's like a cubic function.
It looks like a cubic function, doesn't it? Yeah. Think about the normal sine function. Here's the normal sine function, right? Well, first of all, the sine function, the normal sine function is bounded between -1 and 1, right? Like it does this oscillation, it's periodic, right? This right here, the green one, this hyperbolic sine, what happens if I do sine hyperbolic x? Yeah, okay, I typed in sine hyperbolic x and it just drew it right over the one I typed in. You'll see that? Take it out, put it back, it's the same thing. So these things look completely different, right? It's not periodic, it doesn't repeat itself. It's not bounded between -1 and 1. It does look like it has an infinite domain though. You can plug in any number on this function, it's going to spit something out. If you don't believe that, let me zoom this. Just to show you there's graph. No matter how far out you go. So as you go to the right, it goes up fast though, doesn't it? But you keep on going to the right, there is graph. Okay. Oh, for those of you who use Desmos, I found this the other day. It's pretty cool. What I just did, if you just hover over the y-axis and hit the shift key, it allows you to scale the y-axis without touching the x-axis. And if you hover over the x-axis and go left and right, you can scale the x-axis without adjusting the y. Pretty cool. All right, so that's sine hyperbolic. Got it? Weird function. That's what it looks like. Doesn't look like sine. Let me do the cosine hyperbolic function now. Let's take a look at that one. Cosine hyperbolic. Look at it. It is exactly the same as sine hyperbolic with one very slight difference. It's plus instead of minus right there.
I'm not able to see. Oh, never mind.
Okay. It's this plus instead of the minus. Do y'all see that? That's the only difference between those two. Okay, well, let's see. How does that change our graph? Let's go see. So all I'm going to do is I'll change this one to a different color. Let me do blue here. Let me get the sine hyperbolic out of here. Let's take sine out. Change this to a plus. Okay, so the green is your sine hyperbolic and the blue is your cosine hyperbolic. I mean, this was cosine x. This is sine x. Cosine x and sine x look kind of the same, don't they? They're just like translations of each other. Very similar. Similar in terms of its, its bounded output and stuff for sine and cosine. Do y'all see what these hyperbolics? There's your hyperbolic sine, there's your hyperbolic cosine. They don't look the same, do they? The hyperbolic cosine almost looks like a parabola, doesn't it? Doesn't this blue almost look like a parabola? It does, right?
Yeah,
Okay.
so it is, right?
It's not a parabola. It looks like a parabola, but it's not. I'm gonna talk more about that in a minute. So for now, just think, yeah, it looks like a parabola. All right, now what about tangent hyperbolic? Well, tangent hyperbolic is what you would think it would be. It's just the ratio of the hyperbolic sine over the hyperbolic cosine. So you're still taking, you know, like in pre-cal, tangent is sine over cosine. Well, same thing with hyperbolic tangent. Hyperbolic tangent is just hyperbolic sine divided by hyperbolic cosine. Let's take a look at that one. That one's going to be interesting. What happens if I take sine hyperbolic and divided by cosine hyperbolic? Let's see it. There it is. Okay, so the green one is sine hyperbolic, blue one is cosine hyperbolic, black one is tangent hyperbolic. And then the others are just all the other ratios, right? Cosecant hyperbolic is 1 over sine hyperbolic, secant hyperbolic is 1 over cosine hyperbolic, and cotangent hyperbolic is 1 over tangent, or just the reciprocal, so cosine over sine, hyperbolic. So everything is kind of the way you think. The main idea here is that these functions don't look anything like the normal trig functions, right? They're all very different.
Sir, the tangent, what's it called, hyperbolic, is that one still, that one has, instead of vertical asymptotes, it's horizontal?
Well, it looks like it does, right? It looks like it does have an asymptote. What do y'all think? Do you think this keeps growing, or do you think it's closer and closer to a number? What do y'all think? Does it look asymptotic to you?
Yeah.
It looks asymptotic? Looks bounded on the output? How could
Looks
you
like-
figure that out?
Taking the limit.
You would have to take a limit. Yeah, you would have to take tangent hyperbolic of x, which would be your sine hyperbolic x over your cosine hyperbolic x. Sine hyperbolic x by definition is this, right? Over cosine hyperbolic, which is the same thing with a plus, right? That's the definition. So if you wanted to know, like, what happens as x goes to infinity, you would have to take a limit. You would have to take the limit as x goes to infinity of this expression, which means you could cancel the halves out and then just look at this. If you take the limit here, these two both go to 0. And then this is infinity over infinity. And if you, well, actually, if these go to 0, this is going to give you, the ratio here is 1 because these are exactly the same expression. So it goes to 1. I mean, we could do more detailed work, but this is like a loose, this is me loosely trying to convince you that this does indeed go to 1. That was the question, right? The question was like, is it asymptotic here, right? Okay, so we have these 6 new trig functions, right? We have these new 6 trig functions. Let me motivate this with kind of the first application of this. I'm only going to show you one application of the hyperbolics, but it's a very useful and interesting one. And it's called a catenary. A catenary is basically a wire that hangs between 2 poles. So if you were to take any 2 fixed points and hang a wire between them, right? Anything that's flexible, hang a wire, it would form some sort of shape, right? So like you hang a wire between 2 poles. So imagine that we have 2 poles here. There's a pole and there's a pole, and I hang a wire between the two poles, it's going to take on a certain shape, right? That shape is dictated by gravity, and there's really only one shape it can be. And so for a long time, we were trying to figure out, like, what is that shape? And most people would think, oh, it's a parabola, right? It's a parabola between those 2 points. It's not. If you try and get a parabola, here's a parabola. If I try and make this parabola hang between those 2 points, there's no way for me to do it. I cannot get, well, I can make it do that. But what I'm trying to say to you is that in the real world, if you hang a wire, there's no way you can fit a parabola on top of it. What I usually do when we're like in class, like if we were face to face, I would have the computer graph a parabola for me like this on the board. We'd have the projector on, I would have it graph it. And then I'd get a volunteer from the class and we would get a rope and we'd go up to the board and one of us would hold the rope on one end and the other one would hold it on the other end. And we would hang it, and no matter how we move it, we would not be able to fit the parabola to our hanging rope, no matter how we do it.
So it takes account of gravity and the stresses of material, or?
Well, we are saying that it's like a uniformly flexible wire. Like it can't be stiffer in one area than it is in another. It's got to have like uniform stiffness. Does that make sense?
So, sir, what you're saying is that hyperbolic takes gravity into consideration.
Mm-hmm.
And parabolas cannot be done naturally?
Parabolas are great at modeling things that are flying through the air, right? If you throw a rock through the air, the flight is parabolic, okay? But the only thing acting on the rock is gravity. When you have a wire hanging between 2 points, that's different, okay? Because you have these 2 anchor points, then you have the wire that's being affected by that, right? Like it's being held in place. It's not in motion. So the shape of that wire is not parabolic. It is hyperbolic. It is the hyperbolic cosine. It is a catenary, right? So the hyperbolic cosine function is the function we use to model hanging wires, no matter where they are. I don't know if I'm addressing the question, or am I making sense, Brandon?
No, yeah, it's just interesting to like imagine it and actually apply it somewhere. But
yeah,
no.
now how we came up with that is a different question. And that's beyond the scope of this class because it involves differential equations. And so the way we actually came up with the functions and said, oh yeah, this is the one, that's a different question. Okay, and I can't, unfortunately, in this class, show you how we derive that it is this function. You just have to take it kind of on faith that it is. That a cosine hyperbolic models a hanging wire, okay? And that's useful, right? Because if you're building, I don't know, if you're hanging wires like electric companies, right? Hang all these wires that go from town to town, you know? You see these huge wires, these wires have mass, right? I mean, wires are heavy, right? If you have a 300 section foot of wire, that's, you know, this big, thick bundle of copper, right? And these are heavy. So you'd like to know like how much stress, how much load you have at these points, right? And if you want to know the load there, you want to also know the direction. Wouldn't you want to know the direction? Wouldn't that be useful to somehow have the direction that loads in? Wouldn't that correspond to like the slope of the tangent line? If I wanted to know, let me see if I can run this. For some reason, it doesn't want to write on top of that. There we go. If I found the slope of the tangent line here, that's not very good. Slope of the tangent line there, right? The slope of the tangent line, wouldn't that be a good reference as to figuring out the direction of the force for that load on that anchor point? I mean, and how do we hold wires? This is always blowing my mind. How do we hold these wires to these poles? Like if these are electrified wires, what do we use? You can't hold a wire to a pole with a wire because then the electricity will just go right to ground, right? It'd be a direct short.
rubber, something
We
that,
use some sort of insulator, right? So if you look at wires, right, where they go up to the pole, where it's being anchored to the pole, you'll see this thing that looks like a, I don't know. Let me see, let's look it up. We're going off topic, but let's look up electric wire pole. This is a terrible search. This is not good at all.
just type in electric pole.
Yeah. Electric utility pole. We all see it when we drive down the road. There we go. Ah, here we go. Yeah, okay. That's not exactly what I was thinking about design wise, but hold on. These are all on top. I'm trying to find the ones that. There we go. Nah, that's still no good. Sorry, y'all. I didn't come prepared to show you pictures of utility poles.
So while we're searching, does gravity have like an effect on the shape of the that parabolic function? So like this, like, will it look the same on the moon, like, or on Mars, or if you were on Jupiter?
It'll still be a hyperbolic cosine function.
Got
It
it.
just will have different, you know how even with like sine functions, we can change like the shape by scaling it, you know, stretching it, vertical stretches and horizontals, all that.
Yeah.
Same idea, that it will be a hyperbolic cosine function. It'll just have certain, it's just like if you throw a rock on the moon, it's going to be parabolic. Like the rock will go through the air in a parabolic shape.
Mhm.
So, all right. So this is not a very good picture, but these are the insulators. These are things that the electricity cannot get. The electricity cannot pass through that to the pole. So this, I wish I had a better picture. The electricity is here, right? It comes to the insulator, right? Which is, this is holding it to the actual pole. And then there's a wire. It's hard to see here. This wire loops down and goes back over here and then continues down the line. So the electricity is actually here, looped down, and then back through the line. These insulators are just holding the wires in place, but the electricity can't go through the pole. So if you're building this, you would like to know how much force is on that thing that's holding it, because that's a non-conductive material, which is often ceramic, something that is brittle and fragile. So you need to make sure they can hold the load. So you need to know the direction of the load, which means you need to know the derivative for that catenary. Okay, I'm off topic. The main point is that they are useful, all right? These hyperbolic trig functions. All right, now. Remember the Pythagorean identities? Do you remember the Pythagorean identity? Of course you do. Why am I asking you that question? It's a stupid question. Everyone here knows that sine squared theta plus cosine squared theta is 1, right? I mean, that we've been saying that forever. It's been it was a very useful, it still continues to be a very useful identity. This is another identity we have now involving cosine hyperbolics. It's almost this, right? It's almost this, except there's subtraction. And because there's subtraction, the order matters. So let's show that this property is true. Let's show that cosine hyperbolic squared plus sine hyperbolic squared is 1. You ready? I'm going to show this to you. Here's what I'm doing. I'm going to write down what cosine hyperbolic is first. 1/2 e to the x plus e to the negative x. Everyone agree that's cosine hyperbolic? You know, take that and square it, subtract from it the sine hyperbolic squared, which is 1/2 e to the x minus e to the negative x. Okay, I want to show you that that's equal to 1. Here we go. When I square, because there's multiplication right there at that 1/2, I can square the half and then square the thing in parentheses here, square the half and then square the thing in parentheses. So it becomes 1/4 e to the x plus e to the negative x squared minus 1/4 e to the x minus e to the negative x, that quantity squared. That's just algebra, right? Equals 1/4. All right, I'm gonna have to square this, right? So if I square it, actually, I'm gonna have to FOIL it. So I'm giving myself, I'm writing it all out so I don't make any mistakes. Okay, so I already squared the 1/2, became the 4th. I have not squared this, I'm about to. So I'm going to multiply times itself, and then over here, the same thing. Let's do what's in here first. Here's the 1/4. All right, first multiplication, e to the x times e to the x is, what's e to the x times e to the x? Same base. What do you do to the exponents?
E2x.
E to the 2x. You just add the x's together, right? Add these two exponents. Add them, not multiply, right? So this just becomes e to the 2x. All right, how about this one, here to here? This one is the one that people get messed up on. What's that?
E cancel. E to 0.
E to the 0. What's e to the 0 though?
1.
Anything to the 0 is 1.
1.
Good, so that's 1. So we get +1. What about this middle one? This middle multiplication here to here? Isn't that the same thing? E to the negative x times e to the x.
This is 1.
So e to the 0, so that's another 1 there. And then careful on the last one here, e to the negative x times e to the negative x is e to the negative 2x, right? Because you're adding the
Yeah,
x.
negative 2x.
So plus e to the negative 2x. Now, all of that had a 1/4 in front of it, right? All that had a 1/4. Okay, so I'll take care of that in a minute. Minus 1/4. And then over here, when we do this, it's very similar to what we just got, isn't it? Very similar. The first multiplication gives us e to the 2x. Let's see, Lewis, did I call on you? I feel like I called on Lewis, didn't I?
Yeah, you did, but I can go again.
I want to get through everyone that I haven't. Samuel, how about Samuel?
No, sir, you haven't called on me yet.
Okay, you go by Sam?
Yeah, that's fine.
Okay, I'm going to change it in my thing, so when I call on you, you'll know who I'm talking about. All right, Sam, finish this parentheses out. So I've done this one. What would the next one be?
It would be -1 and -1.
-1, and then the middle one would be -1, and then the last one?
Plus e to the negative 2x.
Plus e to the negative 2x. Good. We have negative and negative. It's positive. All right, this is not so bad, I guess. I don't know. Let's distribute. Here, 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 here. Unless y'all want to put the ones together. You want to put the ones together? Make it a 2.
Sure.
And put these together and make that a -2. And then pass a 1/4 through everything. So 1/4 e to the 2x plus, this becomes 2/4 because you're doing a 1/4 of 2. So 2/4 is 1/2. And then plus 1/4 e to the negative 2x. That's me passing a 1/4 through everything there. And then I'm going to pass a -1/4 through here. So I get -1/4 e to the 2x plus a half, because I have -2 here being multiplied by -1/4. That's positive 2/4. It's positive 1/2. And then finally I have minus 1/4 e to the negative 2x. Gone. 1. 1/2 plus 1. And 1/2 plus 1/2 is 1. All that is just showing you that that identity is true. Right? So just like we had all these identities with sine and cosine and all these important identities, there's a bunch of identities with hyperbolics. We're not going to spend 3 weeks studying them, but you need to know they exist. And here are the important ones. These are on your formula sheets, but you need to know that these are here. We just proved this one. We just did this one right here, but there's a bunch of other ones. All right, so that's all you need to know is that they exist. On your formula sheets, let's go look at it real quick on your formula sheets. So on your formula sheets, if you go to reference page 4, special functions, you can see the hyperbolic functions are here. Okay, so these are on your formula sheets. The definitions are right there. And then properties, I don't see properties. Hold on, let me see if there's properties somewhere else. Yeah, I don't see these properties. I don't think they're listed here. They give you a bunch of the sine and cosine properties, all your important ones, but not for the hyperbolics. I don't see the important properties here. But at a minimum, though, they give you the definitions of the functions. All right, let's move on. Because what are we really interested in here? We're interested in these 6 functions, but we're more interested in what?
The inverse?
Their
The
derivative.
inverse. And then once we get those,
Their
The
derivative.
derivatives.
the derivatives, really, right? Because calculus is about differentiation and antiderivatives also. But really, we want to know if these are functions and we can graph them, can we find the slopes of tangent lines? So you ready to talk about their derivatives? Just as a guess, what do you think the derivative of hyperbolic sine is? What do you hope it is?
Cosine hyperbolic?
You hope it's cosine hyperbolic, right? Because then it would match up with what's happening in trig.
Yeah,
Like
but
the
it
regular
probably
trig?
isn't.
Well, I have kind of good and bad news here. Here they are. We now established the derivatives of these. The derivative of sine hyperbolic is cosine hyperbolic. So you should be happy about that because that matches, the derivative of sine of x is cosine of x. So derivative of sine hyperbolic of x is cosine hyperbolic of x. We're all happy about that. And then we get to the next one for cosine. Say again?
There's no negative.
Yeah, there's no negative here. So this is where things start to become different. You see? Right there, that doesn't have a negative like the regular one, like derivative of cosine is negative sine, not for the hyperbolics. Hey, how would you prove this? How would you prove that this is true? You would take 1/2 e to the x minus e to the negative x, and you would take its derivative, wouldn't you?
Yes, sir.
Okay, take its derivative. The 1/2 comes for the ride. What's the derivative of e to the x? Itself, okay, e to the x. Minus, now very carefully, what's derivative of e to the negative x? Chain rule.
Negative e
1 to the negative x.
Negative e to the negative x. So I would put negative e to the negative x, wouldn't I? That would be the derivative there. Right, because you have to take derivative of e to the negative x, which is itself, times the derivative of what's up here, which is -1. And that's where you get this negative e to the negative x. But it's already being subtracted. So that becomes e to the x plus e to the negative x, right? But that's cosine hyperbolic. Right, that's the definition of cosine hyperbolic. So that's why this is true. And you could show the rest of these the same way. I'm not going to, but you just be aware that these are here and these are also in your formula sheets. All right, so you have these. They're similar to what you've learned. All right, I'm moving on. Why don't you take a minute to do that? I'll scroll up so you can see the derivatives up here. Take a minute to do that one. So it's kind of the same game. Now we have 6 functions. We've got their derivatives. Now we can apply all the different rules, chain rule, product rule, quotient, everything's in play. So see what happens.
Sorry, I had a phone call. What were we doing?
You're doing example 2. I'm giving you what y is equal to, and you're trying to find y prime.
Okay.
I'll take a volunteer to give me the answer.
I am stuck. I'm not gonna lie, sir.
You're stuck? Okay. That's a product, right? So the derivative of this should be the product. We have to do the product rule on this. So first, what's derivative of this one?
It would be 1.
It'd be 1. Okay, so 1, I'm gonna put the 1, we don't need it, times the other one, right? Plus, and then now we need the derivative of this one. That you have to be a little careful with, because the derivative of secant hyperbolic of x, right, is negative secant hyperbolic of x tangent hyperbolic of x, right? So for us, we don't have secant hyperbolic of x, we have secant hyperbolic of e to the x. So we're going to have some chain rule here. The derivative should be negative. Who's got it? Negative what?
Secant
Secant
to the
hyperbolic.
x.
Secant hyperbolic of what?
E to the x.
Of e to the x. Good.
And then tangent hyperbolic e to the x.
Good.
And then it's times is that
Yep.
1, or is it?
No, x is because you're finishing out the product rule,
Yeah.
but you have to take derivative of what's in here.
Which is e to the x. too.
E to the x. Oh, okay.
There we go.
I got mixed up with the derivative of that.
Okay, who has a question? Trying to take, we're doing the product rule. Derivative first one's 1 times the second function, which is this, plus the derivative of secant hyperbolic of something, right? Is negative secant hyperbolic of that something, tangent hyperbolic of that something. And then we go to the inner function, take the derivative, that's e to the x. And now we're done with the derivative of this, but we have to finish the product rule off. So we bring the x into the back. And if you put the x out front first in the beginning, that's fine. Depends on how you learn product rule. This is the way I teach it. So
I wrote e to the x twice, the derivative of the inside. I wrote that twice just because I saw it twice inside that function. So I guess I'll just scratch that out.
You saw the secant and tangent hyperbolic e to the x. That's I did the same thing.
Yeah, so I wrote
okay,
it
so like
twice.
when you were doing the the chain rule, you did it twice because you had it
Yeah,
twice.
because we saw it twice there, yeah.
Yeah, just be careful. You're always referring back to the original function here, and it only appears in here one time.
Yeah.
Any questions? Okay. We move on. Each of these functions, these 6 hyperbolic functions, each one of them has an inverse. All right, each one of them has an inverse. And here's what they are. The hyperbolic sine inverse function of x is natural log of this. Why do you think there's a natural log in the hyperbolic inverse function? Why do you think there's a natural log in there? What did the hyperbolic sine function have it?
Does it translate from the e?
It had e to the x's in it, right? The hyperbolic sine function. So the inverse of that should involve natural logs because the natural log is the inverse of e to the x. So it should not surprise us to see natural log. Now there are 6 of these. There are 6 inverse ones, but we will only look at the 3 of them. We're only going to look at the inverse of the hyperbolic sine, hyperbolic cosine, hyperbolic tangent. All right. I don't think I'm going to have time. Usually, this is a point in class where I actually prove to you why this is true. I'm going to skip it and just move on, and we're just going to take it on faith. If I have time, I'll show it to you afterward. It's really an awesome algebra thing. Let's move to example 3. Oh, that's me showing that. Okay, so I'm not going to show that. I'm going to skip that. Okay, show that the derivative of cosine hyperbolic inverse of x is this. Okay, I'm going to grab this and take it to another page. Okay. I need to go back and grab the definition of cosine hyperbolic inverse. Here's cosine hyperbolic inverse. Plug that in. Let me see. Come on, man. All right, so here's what this example is asking us to do. It's asking us to show that the derivative of this function is this. And here's the definition of that function, right? This is the definition of what cosine hyperbolic inverse is, which means all we have to do is take derivative of this in green. So let's do that. Take natural log of x plus the square root of x squared minus 1. Take all of that and take its derivative. So this is going to require chain rule, right? Arturo, you there?
Yeah.
Okay, Arturo, what's the derivative of natural log of anything, Arturo?
1 over that anything.
1 over that anything. So that's 1 over x plus the square root of x squared minus 1. Good, Arturo. What's next? What do we have to do next?
Don't you have to take the derivative of what's in the square root?
Yeah.
Or what's in that anything I meant?
In that
Yeah.
green, the whole thing, right? Go
Yeah.
ahead. How are you going to, what's the derivative of all that green stuff?
1 plus 1 over 2 square root of x squared minus 1.
Yes, you're good.
And
Keep going. You're missing something on that.
Is it the square root? I have to take the derivative of that.
You have to take derivative of what's in it.
Okay, so 2x.
2x. Good.
Times
good.
2x.
All of that's in parentheses, right? So what Arturo did again, derivative natural log of this green junk is 1 over the green junk. Times, then Arturo said, you got to take derivative of the green. I have addition. Do the derivative of x, 1 plus. Derivative of the square root of something is 1 over 2 times the square root of that something. But then you have to take derivative of the square root of what's underneath the root, which is the 2x. So that's all chain rule Cal 1 stuff. These 2's cancel. And we're left with 1 over x plus the square root of x squared minus 1 times, what's over here? Times 1 plus x over the square root of x squared minus 1. Like that. I'm supposed to show that it's equal to this, right? What can we do? What can we do? Common denominator? Well, we have two choices. We can distribute this through, or we can put these two together with common denominator. What do you want to do? I don't care. We can do either one. Common or distribute?
Let's see common.
Common?
Mhm.
Common is what I heard. So let's do that. Let's put these two together, which means I need to rewrite this 1 as a what? Root x squared minus 1, root x squared minus 1. Right, that's the one that used to be there, but I need these to have the same denominator. So when I do that, I get 1 over x plus square root x squared minus 1 times, now put these two together. So they'll have a single numerator, square root of x squared minus 1 plus x over the common denominator, square root of x squared minus 1. Any questions on me putting these together algebraically? Do y'all see what happens? Those are
They
exactly
cancel
the
out.
same. I'm sorry?
Oh, I was too late, but I was saying they cancel out.
They cancel out. Okay, that's what I thought I heard you say. Okay. 1 over square root of x squared minus 1. Bam, check. That's what we were trying to show. All right, that was just showing what the derivative of one of those are. Obviously, we could do it for the rest. So that's where the notes say, hey, look, you know, here the derivatives of these inverse hyperbolic trig functions can be found on your formula sheets, basically. So go to your formula sheets. This is kind of it. I mean, we are at the end of, you know, here were the hyperbolic, the 6 new functions today. Here are their inverses. And then we're most interested in the derivatives. So here at the last formulas 25 through 36 are your 6 hyperbolic functions derivatives and your 6 inverse hyperbolic function derivatives. So now we have a grand total of 12 new derivatives for today. I just proved this one to you, right? And I actually proved this one to you also. But that's it. We are complete when it comes to all the functions that we are going to use in this calculus sequence. So we've got a loaded toolbox. We've got all of our algebra skills. We've got everything ready to go. We know how to take derivatives. We know how to use the chain rule. We know how to do implicit differentiation. And now we're ready to really get into the Cal 2. All right. Questions? If everything kind of seems a little like this isn't what you expected in Cal 2, you expected something different, it's about to change. Okay, it's going to be apples and oranges in the next day or two. All right, so we're kind of done with all of the ancillary stuff, just like getting this out of the way. Now let's get into the main goal, which is antiderivatives. Let's see here. I'm wondering with the next 15 minutes, if I do this application, I want to see if you can handle that word problem on your own. I really don't want to do it. I want to see if you can. Let me just look at the homework real quick. Yeah, there's some, it asks to prove some identities in here in this homework. 26 through 41 is really the derivative part of the homework, where it gives you functions, you take derivative, practice chain rule, all that. 47 and 48. Oh, 48. I usually have students ask me about 48. Yeah, so I definitely want you to try these two problems, 47 and 8. Try them, okay? See how you do. Ask questions, but I mean, do all your other homework first. Do everything leading up to it before you get to those problems. All right. There's a problem in the beginning here that is, I don't want it to like freak you out, okay? Because it's a lot easier than it looks. Like if I were to ask you right now, you know, what's cosine hyperbolic of 3? You don't get your calculator out and do cosine hyperbolic, right? What you do is use the definition of cosine hyperbolic. Cosine hyperbolic of x is 1/2 e to the x plus e to the negative x. That's the definition, isn't it? So cosine hyperbolic of 3 is 1/2 e cubed plus e to the negative 3. Whatever that number is, you'd have to use a calculator to get a decimal answer. But that's what cosine hyperbolic of 3 is. So the first few problems in here are just asking you to do things like this. Plug numbers in and, you know, just make sure you know how to use the formula. There's no calculus involved in that. Okay, I've got 10 minutes, so I think I have enough time. I want to show you all this example. I want to show this is true. This is me trying to prove to you what the definition of an inverse hyperbolic trig function is. Remember, this is not a derivative, right? This is just, hey, I'm trying to convince you that this is true, all right? The one thing that we need in order to do this is we need to remember what sine hyperbolic of x is. That we have to know, which here was the definition. Right, that's what sine hyperbolic of x is. And now I try and show you that the inverse of this function is this function. You ready? I've got 11 minutes. Let's see what I can do. The reason I show this to you is because there's one particular part of this that you probably have not ever seen before. And I want you to see it because it's kind of neat to see it. All right. So I'm trying to find the inverse of this function. Do y'all agree with that? This function in blue, I'm trying to find its inverse. Do y'all remember how we did that back in college algebra? If somebody gave you a function and they say, hey, go find its inverse. Do you remember the steps to do that? Let me remind you, I see a lot of shaking heads. No. Let's say I gave you this function, f of x is 3x plus 1. And I asked you to find the inverse. Let me show you what you do. Replace f of x with y. Replace x with y and y with x. Switch their positions. So make this x, make that y, and then solve for y. Does this sound familiar now that I'm doing it? Go solve for y. So now I subtract 1 on both sides, and then I divide both sides by 3. And since I have solved for y now, this is my inverse function. Okay. So the way this works is this. If you give me an x, send it through the function, it's going to spit out some value. So let's just take this function. Let's just plug a value in. How about 3? Let's plug 3 in there. If you take 3 in and you plug it into this function, what does it spit out?
10.
10, thank you. And now if you take 10 and you take that 10 and you plug it into the inverse function into
give you
here,
3.
what happens when you plug 10 in here?
It'll give you 3.
You get 3. Oh, 3. So it sends it back to 3, right? That's what the inverse function does, right? It sends it back to where it came from. That's exactly what I'm trying to do right now. I'm saying, here's this function, hyperbolic sine of x. Show me that the inverse of this function is this function. So I'm going to start with this, okay? Is it all right, everyone, if I call this up here, call it y? And now, once I call it y, I switch the x's and y's, right? Everywhere I see a y, put x. Everywhere I see an x, put a y. And this is where we start to run into problems. Because now I have to solve for y. Anybody have an idea of how I can solve for y here? I need to get y by itself.
Take the logarithm of the.
So the log will kill off e, right? But if I do the logarithm right now, what's going to happen? Like if I just do log right now, log of the left, log of the right. Well, the left side is log of x, right? But on the right-hand side, I have log of a product, right? Can you split a product up with logs? Remember properties of logs? Log of, let's say, m times n. Can you split that up if you have multiplication? You can, right? There's a property, log of n, I'm sorry, m. Products become addition of two logs. That look like a familiar property? And if there was division in there, what would we have done?
It'll be
Subtract, right?
subtraction. Yeah.
Subtract, right? But is there a property for logs that says if you have addition inside, that you can do anything with it? No. Okay, there is no property that allows you to split up addition or subtraction in a log. So right now, here, I do have multiplication. You all see this times this? Oops, I'm missing a parenthesis here. So I could split that into two logs. Plus natural log of e to the y minus e to the negative y. I could do that on the right side. But the problem is this. I can't do anything to this. This natural log does not kill off both of these e's. And I can't split it up because I don't have a property that allows me to. Do y'all see the problem I'm having? Algebraically, this is an issue. I don't have a way through this right now. So even though the natural log seems very natural, and we will use it, it just can't be yet. We just can't do it yet. Okay, so this ain't gonna work. I don't want to erase it. I'm gonna just move it to the side. Okay, that didn't work.
So we gotta find the derivative in terms of y.
Well, if we find the derivative now with respect to y, that still doesn't tell me what that would be kind of like we're not following the procedure anymore, right? Like this procedure is replace y with this, switch them, and then solve for y. Like we never took a derivative at this point. So we're still trying to follow this procedure, and that means get y by itself. So look at, we only have 5 minutes. In all my years of teaching Cal 2, which has been, 20 years now, I have not had a student ever solve this, okay, for y correctly. So I'm gonna just get to it, all right? If we had time, I would put you in groups, I'd have you think about it, I'd have you throw some, and people start to get close. No one's ever gotten all the way, but let me just show you it, all right? So here's what we're gonna do. We're gonna multiply both sides by 2, all right? That's just to clear the fraction out, no big deal. All right. Then I'm going to do something very, very unnatural. I'm going to multiply both sides by e to the y. All right, now let's see why I'm doing that. Let's see what happens. So on the left side, nothing happens. We just get e to the y times 2x. On the right, distribute. What's e to the y times e to the y? Well, we've done that earlier today, right? You just add the exponents. So
Yeah,
e to the 2y minus now this one.
It'll be 1.
That's 1. Okay. Now I'm going to bring everything to one side of the equation. And I'm going to write it in a certain order. This is where some students start to see maybe where I'm headed with this.
Will you use U sub?
I'm going to do kind of like a U sub here. I'm going to make a substitution. You got to see here that I've got like, this is e to the y squared minus, I'm going to write it this way, 2x e to the y minus 1. And what substitution, Ricardo? Just e to the y, right?
Sorry, yes, it's e to the
E to
y.
the y, you want to replace e to the y with u maybe, something like that?
Mhm.
Okay, so if we do that, we have u squared minus 2xu minus 1. That's weird, right? That's weird, what we're doing. Does anyone know where I'm going to go now? Let me ask you this.
Factor it.
If I could factor it, I'm not going to be able to, but what do we have if we can't factor?
The equation,
You can complete the
The
square
quadratic formula. So look,
or that.
remember this formula, everyone? Of course you remember this formula. I mean, right? Uh-oh, I can't remember it. Negative b plus or minus the square root b squared minus, shit, slow down, Robert. 4ac, I'm just watching the clock here. All over 2a. Everyone knows this formula for quadratic, right? If you have a quadratic where your variable is x, right? And a, b, and c are the numbers in front of the x squared x and then the constant term, right? That's the formula you use. That's exactly what we have here, except that our variable is u, not x, but u. And instead of having a, b, c being constants, our a here is 1. What's our b?
2x.
Negative
-2.
2x is our b. And our c is what? Negative 1. I don't think, it's probably never happened in the past where you use the quadratic formula on a quadratic that had more than one variable in it. It's always usually just been x or just a single variable, and your a, b, and c have always been numbers. In this case, your a, b, and c are going to be, well, some numbers, but also variables. So according to the quadratic formula now, this is going to be u, the solutions to this equation are negative b. What's negative b for me? Negative b, b is nothing. Positive 2x plus or minus the square root of b squared, which is that thing squared, right? Which is 4x squared. Minus 4, what's a times c? Negative 1, right? So this is going to be times negative 1. I'm out of time. All over 2 times 1. Okay. If you have to go, you got to go. I'm recording this, so it'll be there if you want to go back and watch the end of this. I'm going to keep going because I want to finish this. So I've got u. What was u? Ricardo had said that u was e to the y, right? Okay, so this is really e to the y equals 2x plus or minus the square root. Ooh, wait a minute. Isn't that going to be 4x squared plus 4 in there? That's what this is?
Yes.
And I can pull a 4 out of both of those. And if I pull a 4 out of both of those, it can come out of the root as a 2. And I'm still left with x squared plus 1. And on the bottom, I have a 2. So they all have 2s, don't they? So e to the y equals x plus or minus the square root of x squared plus 1. And there's no more denominator. One more step. Get this y by itself. How do you get y by itself now?
Len.
The natural log.
Natural log.
See, now we're going to do it. Natural log here, natural log here. And then the left side becomes y. The right side is natural log of x plus or minus the square root of x squared plus 1. And that's what we were trying to show, I believe, right? Isn't that it? With one little thing. What's the difference
There's no
between our
minus.
answer and our answer? What's that?
There's no minus.
There's no minus. Now, the reason why there's no minus is because remember with natural logs, you can only do the natural log of a a positive number. You can only have positive numbers in there in a natural log. And if you think about x, whatever x is, if you were to try and subtract this number here is bigger than x. I mean, if you took the 1 away, just imagine that 1 wasn't there. Wouldn't this just be x? If this 1 wasn't here, imagine that 1's not here. That's just x, right? But by adding 1, that guarantees that this number here, square root of it, is bigger than x. So if I take x and subtract a number bigger than x, it'll give me a negative, which I can't do. So I throw out the negative sign and I only do the positive. All right. Your homework is just 3-6. You don't have to turn anything in by the next time we meet, but I definitely would expect that you would do the homework for 3-6 before we see each other again. All right. I'm headed straight to my office hours. I'll be there for, I don't know, forget what it is, 20, 30 minutes or something. All right. Thank you everyone for your attention. Get into the antiderivatives next time.
Thank you, Professor.
Okay, take care.
Thank you.
You're welcome. Thank you.